right, everyone. So for the last in our introductory series of gas loss problems, here we have an example of Gay-Lussac's law. Joseph Gay-Lussac was the French scientist who came up with this law, which talks about the relationship between pressure and temperature. So we're assuming that we have a rigid container, we have a gas where the volume doesn't change. So imagine like a metal container where you can't crush it, you can't expand it, it's going to stay the same volume no matter what. Under those conditions, what Gay-Lussac discovered, and he worked with other scientists to figure this out, was that the pressure is directly proportional to the temperature. That is, as the temperature increases, the pressure also increases. So, what we're going to look at here is a gas with a pressure of 699 millimeters of mercury at 40 degrees Celsius. And it's asking us, what is the temperature at standard pressure? Now, there is a value called standard temperature and pressure, or STP, that you're going to want to know, and usually will be provided for you when we do these problems. But for now, I'm just going to give you the pressure part of standard pressure, because I might be giving something away if I give you the temperature at standard temperature and pressure. So standard pressure is, I'm going to go ahead and write this up here. Excuse my dog in the background. The puppy's very excited about something. The standard pressure is 760 millimeters of mercury, which also happens to be equal to 1 atmosphere of pressure. It's normal atmospheric pressure. So I'm going to go ahead and put that in a box up here to separate it, and then we're going to talk about the equation that we use for Gay-Lussac's law. So Gay-Lussac's law is very similar to Charles' law in the relationship between the two quantities. They are directly proportional. So the equation for Charles' law involved two fractions, and that's exactly what we're going to see here. We're going to see P1 over T1 is equal to P2 over T2. So, again, we're always going to plan out our problem. This is going to be a great rule of thumb for the rest of the year because, spoiler alert, there is quite a bit of math coming up the rest of the year. And planning out your problem is going to make your life so much easier. So we're going to look at the first sentence to find our initial conditions, and we see that P1 is equal to 699 millimeters of mercury. And we also see that temperature is 40 degrees Celsius. Now, keep in mind here that we're going to make sure that we put that temperature in Kelvin before we plug it into our problem. So the way we do that is we add 273 to the temperature in degrees Celsius. So 40 plus 273 gives us 313 Kelvin. So we start at a temperature 313 Kelvin, and we're asked what is the temperature at standard pressure. So that means what is the temperature means we don't know T2. We don't know what the temperature changes to. We do know, because we know a little bit about standard pressure, or it may be given to you, that standard pressure is equal to 760 millimeters of mercury. So now all that's left to do is plug and chug. So P1 over T1. Actually, I'm not gonna rewrite the equation just yet. I'm going to go ahead and just plug in these numbers. So 699 over 313 is equal to 760 divided by T2. So we're going to cross multiply just like we did the last time. Anytime you have two fractions like this, cross multiplying is always the move. It's going to make your life a whole lot easier. And so on one side we have 699 times T2 equals 760 times 313. And so we're going to get a very big number over here on the right. And I always recommend writing this number down so you don't enter it incorrectly or forget it. This big number is 237,880. And on the other side, we have 699 divided by T2. We're going to divide both sides by 699. And I think I might have enough room to write the solution on the bottom this time. So 237,880 divided by 699 is going to give us that temperature in Kelvin. And that temperature in Kelvin is equal to 340 Kelvin. Now, if I did not specify a unit for the temperature, then any unit you give me for temperature is completely fine. So if you give it to me in Kelvin or convert it to degrees Celsius, either way is totally fine. If I do specify, occasionally I might specify, give me the Celsius temperature, because again, that's the temperature that sort of normal people use outside of science. All you got to do to get the Celsius temperature is to subtract 273. And when we subtract 273 from 340, we're going to get a final Celsius temperature of 67 degrees Celsius. And so to check our answer, we're going to make sure that our answer obeys Gay-Lussac's law. We would expect that the temperature would increase as the pressure increases, and to get it up to standard pressure, we would have to increase that pressure from 699 to 760. And it does look like the temperature rather increases from 40 degrees or 313 Kelvin to 67 degrees or 340 Kelvin. So the math seems to check out. The answer makes sense, and I hope that this demonstration of Gay-Lussac's law is helpful. Have a great day.